A 75 ohm coaxial transmission line has a length of 2 centimeters and is terminated with a load impedance of 37.5 plus J 75 ohm. If the dielectric constant of the line is 2.56 and the frequency is 3 gigahertz, find the input impedance to the line, the reflection coefficient at the load, the reflection coefficient at the input, and the SWR on the line. Since we are going to be using a Smith chart, we need to normalize our load impedance. So load impedance is equal to 37.5 plus J75 ohms. We need to normalize it to the transmission line, which is 75 ohms. So just divide this by 75. So ZL is going to equal 0.5 plus 1J. This is our normalized. So ZL bar. Let's also find the electrical length of our transmission line. So, lambda is equal to the speed of light over the dielectric constant multiplied by the frequency. So that's 3 times 10 to the 8th over square root of 2.56 multiplied by 3 times 10 to the 9th. This value would just equal 6.25 centimeters. So that's just the length is equal to lambda over 6.25 centimeters. 6.25 centimeters. But we multiply this by 2 centimeters because in the problem it states the transmission line has a length of 2 centimeters, but that length isn't our electrical length. We need to also take in the dielectric constant of frequency to get that. So then our actual electrical length would be just, so 2 divided by 6.25 is 0.32 lambda. So this is our electrical length of the transmission line. So now let's move on to the Smith chart. So this is 0.5, and this is 1. So ZL, our load, is going to be right here. Ooh, just mark that real fast. Right here. So that's our Z. Just normalized. Now, we are going to draw a line to the origin. So if we do that, let's just insert this. So from ZL to the origin, that is going to be a row. Okay, so this value is rho. We take that length, rho, and we come down to this radially squared parameters to find our VSWR value and our reflection at load magnitude. So if you take that length and then bring it down, so I'm just going to use a piece of paper and come down, measure that, and then from the center, so the center, it's right here, right? So we're going to measure that length from the starting point to the end point, and we get something about right here. So our VSWR is equal to about 4.5, and our reflection at load, so that's right here, and then our reflection at load will be right about here, so that's like 0.62. Now that's the magnitude of our reflection load, load reflection. So then we're gonna go up. Let me just erase this. Okay. Let's go back up to the line that we drew from the origin to ZL. So to find the angle of our reflection load, we would just need to extend this line. So the angles are read from here. So it's somewhere between 90 and 80. Somewhere between 90 and 80. It's about, let's just say, 83 degrees. So our reflection at load is going to be with the magnitude of 0.62 and a phase of 83 degrees. Okay, so we did that. Now, to get our Z in, we just need to add the electrical length that we calculated. So our electrical length that we calculated was 0.32 lambda, right? So at our starting point for ZL, it's going to be like 0.138. This is the starting length. This is called the wavelength towards generator. So to our load, we're going to add, that was plus 0.32 lambda. This just equals 0.458. Okay, so now we're going to move in the clockwise direction along the transmission line. So we're going to find the value of 0.58. So 0.58, I'm just going to say it's like right here. Actually, it's a bit closer. So like right here. That angle would just read, I'm going to put it right here. So at reflection in, the angle would be about negative 147. It's negative because it says it's negative, and it's on the other side of the axis. And then to get the magnitude is just going to be the same, 0.62, because we're only moving the phase and not the magnitude. Now, to get Z in, we would just extend that line. Let's just add a line. So from about that point to the origin, right? Okay. And then we want to, this row should be the same because that's our constant resistance circle. So the row needs to be the same. So I'm just gonna take a piece of paper because I don't know how to do it. So I'm just gonna take a piece of paper. So that length rho, it's about that point. So that's our Zn. That's our Zn. So our Zn reads, it's like, the real part is 0.25, and the imaginary part is negative 0.28. Yeah, let's just say 28. So that's our Zn. I'm just gonna. So we actually, since it's normalized, to get Zn unnormalized, we just multiply by 75, I believe, right? Could we divide by 75? Yeah. So multiply that by 75. So 0.25 multiplied by 75. That's 18.75 for the real part. And then the imaginary part, that's 21. So minus 21J. So that's our Zn. So the question was asking, find the input impedance to the line, Zn, or input impedance, the reflection coefficient at the load, that is right here. Let me just circle it. Reflection coefficient load, and then the reflection coefficient at the input right there, and then our VSWR, which is 4.5. So I'll just go over the steps real fast just to review. So first we normalize our Z load, and then we plot it on our Smith chart. This is our real part, and then this circle right here is our imaginary. So we find 0.5, then we find 1. We make that point, which is our ZL. From ZL, we draw a line to the origin, and that's always for the constant resistance circle. That is our line for the constant. Wait, no. I think that's, yeah. So real quick, I'm just going to review the steps again. So first we normalize our load, and then the real part is on this axis, and then our imaginary part is over here. So along the constant resistance circle, we find 0.5, and that's the point right here. Oh wait, and then a real part is 1, and so that 1 is right here, so that's our point on the constant resistance circle. And then from that point to the origin, that's our rho. And if we were to just take a rho, like if we, this radius, and we just made a circle, that circle would be our constant BSR circle. Constant BSWR circle. That would be our BSWR circle. So like this circle has the same rho, so it has the same radius. So after that, we would take that length, come down to our radial scaled parameters, and start the length at the center, and then the end of the length would come here, and then we would read off our VSWR and our reflection at load. Now, the reflection at load down here will only give you the magnitude. To get the phase part, extend your line of the normalized impedance, the L, and you would get your phase from here. Okay, so you get your phase at 83 degrees. Then we need to add the transmission line to our ZL, and that would give us our ZN. So when we're adding the electrical length of 0.32 lambda, we get 0.548. And we're moving in a clockwise direction. We come down, try to find 0.58, found 0.58. And that line we're gonna extend that to the origin. Once we do that, we can actually just read off the angle at 0.458, and that's about negative 147 degrees. So our reflection in would have a magnitude of 0.62, but a phase of negative 147 degrees. So then we want to find Zn. So Zn would just be, so to get the point Zn, remember that the length, it's going to be along the constant VSWR circle. So this is rho 2. So we measure this and then bring it to this side, because that's where we drew a line for our Zn. But to find the actual point, just take the point from the origin. We'll take that length from the origin, and we get it about right here. And then we read off that point. The real part is 0.25. Imaginary part is negative 0.28. But since that's just normalized, we multiply it by 75, and we get our answer as Cn is equal to 18.75. Oh, this is just negative. I don't know why I put it here. So we don't need this, a plus sign. Minus 21J as our answer. And that's it.